Welcome to the video help with physics problems for Physics 1B. In this video we're going to be covering homework set 2, part 1. That's everything under the heading electric potential. For 1221 students this will cover questions 1 to 5. For 1231 students this will cover questions 1 to 8. Problem 1. Part A of this problem says, do electrons tend to go to regions of high potential or of low potential? Well, electrons tend to go to regions of high potential. So we draw our electric field lines going from positive to negative. A positive charge would drop down to this region of low potential down here, whereas an electron will naturally move up to this region of high potential up here. Part B, can two different equipotential surfaces intersect? No. We can't have one point in space with two different potentials. Each point in space can only have one potential, and so we can't have two different equipotential surfaces intersecting. Part C says if E equals 0 at a given point, must the potential equal 0 for that point? Give some examples to prove your answer. No, imagine a positive charge like this and a positive charge over here. Now halfway between them there is no electric field because a charge placed here will not feel a force because it's equally balanced by these two electric fields. However, there is a potential here. The potential actually adds for these two because potential is a scalar, not a vector quality. So this is one example of a case where the electric field is 0 but the potential is not 0. Part D says if you know E at a given point, can you calculate V at that point, and if not, what further information do you need? Well, the potential difference between 2 points is given by the integral between them of E dot ds. We've got a negative sign at the front. So to work out the potential at a point, what you need to know is the electric field along a line. So you need to be able to integrate this here along some line ds. You'll also need to know the potential at one point. Generally we say at an infinite distance the potential is given by 0. Part E, if V equals a constant throughout a given region of space, what can you say about E in that region? So we've got V is constant. So differentiating this dV ds, if this is constant throughout space, then this will equal 0, which will tell us that E is equal to 0, i.e. the electric field is 0. Problem 2. In this case, we are given the distribution of charges and we're asked to derive an expression for the work required to put the four charges into the arrangement indicated in the diagram. So what we need to do is put the charges down one by one, and as we put each one down, work out how much work we need to do. So let's call this one charge 1. It's plus Q and it's placed at the corner of a square here. Initially, when we place it down, there's no existing electrostatic field, so we don't require any force, and so no work is done. So no work is done. It's done to place the first charge. So let's put W1 is equal to 0. Okay, now we place our second charge. It's here, it's got a charge minus Q, it's charge number 2, and it's a distance A from the first charge. Now this first charge has created an electric field, so we do require a force to bring this charge in from an infinite distance and place it here, and so we will require work. So the work done is equal to Q delta V, and this is the change in the voltage, the potential, from an infinite distance to this distance here from the charge plus Q. So this is equal to, okay, now this Q here is the negative Q, it's the charge that we're placing, so this is minus Q, and then we've got to multiply it by the voltage which is created by the electric field of this charge here. So this is Q over 4 pi epsilon naught, and then the distance is A. And so this is equal to minus Q squared over 4 pi epsilon naught A. Okay, now we place a third charge. We place it down here. It's got a charge plus Q. It's a distance A from charge 2, and it's a distance root 2A, just using Pythagoras, from charge 1. So W3 is equal to Q delta V. And we've got two contributions. We've got the contribution from the electric field generated by this one and by this one. So we've got Q times 1 over 4 pi epsilon naught minus Q over A. And then we've got this one as well, which is plus Q squared over 4 pi epsilon naught root 2A. And then finally we place our fourth charge down here. This has a charge minus Q. It's a distance A from charge 3, a distance A from charge 1, and it's a distance root 2A from charge 2. And so W4 is equal to Q delta V, which is equal to minus Q squared over 4 pi epsilon naught A plus Q squared over 4 pi epsilon naught root 2A minus Q squared over 4 pi epsilon naught A. And now the total work that we need to do is just the sum of W1, W2, W3 and W4. Okay, so there's 1, 2, 3, 4 terms, which are the Q squared over 4 pi epsilon naught A terms, and then there's 2 of these terms. Okay, so let's just simplify this a bit. We can cancel out that 4, this 2, and so we've got Q squared over pi epsilon naught A, and here we've got 1 on 2 root 2, and here we've got minus 1, that's this term. And so if you want, you can evaluate this part with the pi on the calculator, in which case you get minus 0.21 Q squared over epsilon naught A, or you can just leave it in this form. Problem 3. Consider a point charge Q is equal to 1.5 times 10 to the minus 8 coulombs. What is the radius of an equipotential surface having a potential of 30 volts? So here we've got a 30 volt surface, and we're asked what's this distance R equal to. So to do this one, we can just use the equation V is equal to Q over 4 pi epsilon naught R. And so we have 30 is equal to 1.5 times 10 to the minus 8 over 4 pi times 8.85 times 10 to the minus 12 times R. Just rearranging this to get R by itself, and we end up with R is equal to 4.5 meters. And then part B, are surfaces whose potentials differ by a constant amount, say 1 volt, evenly spaced in radius? Well, no. The voltage is proportional to 1 on R. So if we wanted them evenly spaced in radius, we need this to be a linear function, and at the moment it's a hyperbolic function. No, because this is an inverse relationship, not a linear relationship. Problem 4, and this is a 1, 2, 3, 1 only problem. Okay, in this problem we have a series of charges. We've got plus q here, and then we've got a minus 3q over here, and we're considering points A and point B such that there's a distance D between points A and B, and A between the charges and the points, like this. And it says derive an expression for VA minus VB, and does your result reduce to the expected answer when D is equal to 0? Okay, so VA, this is equal to Q over 4 pi epsilon naught times this distance, which is A. And then at A, we've also got the potential due to this charge, which is minus 3q over 4 pi epsilon naught. And the distance between A and this charge is D plus A. And VB is equal to, so we've got the electric field due to this Q charge, so Q over 4 pi epsilon naught, and the distance there is A plus D, minus 3q over 4 pi epsilon naught, and the distance here is A. Okay, so we've got VA minus VB is equal to, let's add these two together. When we do a minus, this minus will become a plus, so we'll have Q plus 3q over 4 pi epsilon naught A, and then we've got these terms, so we've got minus 3q, and then this is a minus, so minus q over 4 pi epsilon naught A plus D. Okay, so this is clearly a 4q, and the 4's will cancel out. This will also be, this, if we put brackets like that, this is a 4q, and those 4's will cancel out as well. And so we end up with q over pi epsilon naught, 1 on A, minus 1 over A plus D. And so we can write this as q over pi epsilon naught, common denominator A outside of A plus D, and then A plus D minus A. So this is equal to QD over pi epsilon naught A plus D. So as D goes to 0, we expect VA to go to VB, and so that implies that VA minus VB should be going to 0. And if we put in D equals 0 here, we do get that this is 0, so it is what we expect as D goes to 0. Problem 4 for 1, 2, 2, 1, or 5 for 1, 2, 3, 1. Okay, in this problem we have a rectangle. We have a charge placed at this corner. This is Q1, which is equal to minus 5.0 times 10 to the minus 6 coulombs. At the vertically opposite corner, we have charge Q2, which is equal to plus 2.0 times 10 to the minus 6 coulombs. And then we have a point A, and we have a point B. And this distance here is 5.0 centimeters, and this distance along here is 15.0 centimeters. And in part A, we're asked, what is the electric potential at corner A? So what's the electric potential here? So VA is equal to the sum Q1 over 4 pi epsilon naught, well, let's call it D1. This is D1, the 15 centimeters, and here's D2, which is the 5 centimeters, plus Q2 over 4 pi epsilon naught D2. So this is 1 over 4 pi epsilon naught Q1, which is minus 5.0 times 10 to the minus 6, over the 15 centimeters, 0.15, plus 2.0 times 10 to the minus 6 over the 5 centimetres, 0.05. This is 8.85 times 10 to the minus 12. And so solving on this on the calculator, we get 5.99, 6.0 times 10 to the 4 volts at A. Okay, part B. In this part, we're told that we have a third charge, Q3, which is equal to plus 3.0 times 10 to the minus 6. And we want to move it from B up to A, and we're asked how much work is involved in doing that. Well, work is equal to Q delta V. So the Q which is moving is the Q3, and the change in the voltage is the final voltage VA minus the initial voltage VB. Okay, so we know Q3, we know VA from here. So what we need to do now is calculate VB. So VB is equal to, just substituting into this equation as we go, we've got minus 5.0 times 10 to the minus 6 over 4 pi epsilon naught, and the distance here is the 5 centimetres, so 0.05, plus we've got this charge over here, so this is plus 2.0 times 10 to the minus 6, 4 pi epsilon naught, and this distance is the 15 centimetres, so that's times the 0.15. Epsilon naught, just substituting in 8.85 times 10 to the minus 12. Entering all that into the calculator, you should end up with minus 7.8 times 10 to the 5 volts. Now what we can do is we can substitute everything in here. So this is 3.0 times 10 to the minus 6 for the Q3. VA is 6.0 times 10 to the minus 4 minus VB, so that becomes a plus 7.8 times 10 to the 5. And then solving that, we end up with 2.5 joules, which is a positive number, so that needs to be done on the charge. Done on the charge. As we're moving a positive charge, so this is closer to another positive charge. Part C says, in this process, is external work converted into electrostatic energy or vice versa? Well, we're doing work on the charge, so external work is being converted into potential energy. We need to put energy in to move that charge. Problem 6, which is a 1, 2, 3, 1 only problem. Okay, in this problem we have a point P, which is a distance y above a line of length L and charge density lambda. And we're asked in part A to calculate the electrostatic potential, chosen to be 0 at infinity, at point P in this diagram. So let's consider an element here of this line with length dA, which is a distance A from P. Well, the contribution to the potential at P, dV, is equal to the charge, which is dA, which is the thickness of this, the length of this little element, times the charge density, so dA lambda, that's the charge, over 4 pi epsilon naught times the distance, and it's a distance A from the charge. So if we want to work out the total voltage at point P here, we're going to have to sum up the contribution of each of these little increments like this. So we have V is equal to the integral. Now we're summing up from A is the distance from point P. So down here the distance is L plus Y, and up here the distance is Y. So we're summing up all the little intervals from Y to L plus Y. So from Y to L plus Y. Now lambda is a constant, so we can pull it out the front, and 4 pi epsilon naught are also constants, and so we're left with the dA over A. So when we integrate this, we get a log function. So this is lambda over 4 pi epsilon naught. And now it's log of a from L plus y to L. So that is, to y. So that is lambda over 4 pi epsilon naught log L plus y minus log y. And so because we're subtracting logs, we can just divide inside the log. So we've got lambda over 4 pi epsilon naught log L plus y over y. And so that is our voltage at P. Now part B says use the result of A to compute the component of the electric field P in the y direction along the line. So we've got the voltage is given by minus the integral of E dot ds, and we're looking at the integral along this line. So we can write this integral in a differential form as well. We can write dv dy, we'll replace this ds with a dy as we're considering the increments along this way. So this is equal to minus e. So this is telling us that if we take the derivative of this with respect to y, we will end up with minus the electric field. So we better start with this step here as it's easier to differentiate. So dv dy, we've got this constant out the front, lambda over 4 pi epsilon naught. Now when we take the derivative of log L plus y, we end up with 1 over L plus y. Then when we take the derivative of this, we keep our negative sign and we end up with 1 over y. So this is equal to lambda over 4 pi epsilon naught. And then we've got y, L plus y, common denominator. We end up with y minus L minus y. And so this is equal to minus L lambda over 4 pi epsilon naught y L plus y. And this, we're told up here, is equal to minus e. So let's just steal a little bit of space here. This tells us e is equal to L lambda over 4 pi epsilon naught y L plus y. So we've derived our expression for the electric field there. This is just in the y direction. This only gives us the y component of our electric field. Now in part C, it says determine the component of the electric field at P in the direction perpendicular. So now we want to look along this line. What is the component of the electric field? So this voltage only depends upon y. There's no x dependence. So when we take the derivative of this with respect to x, say, we'll end up with 0 because it's just got no dependence, which tells us that the electric field in that direction is equal to 0. So E of x is equal to 0. Problem 5 for 1221 or 7 for 1231. Here we have a point charge of plus 1.16 microcoulombs. Consider point A, which is 2.06 meters from it. So here's A. And point B, which is 1.17 meters from it, in a direction diametrically opposite. Okay, so here's point B, and that's 1.17 meters. A says find the potential difference, VA minus VB. Okay, all we need to do is substitute in. We know V is equal to Q over 4 pi epsilon naught R, where R is the distance from the charge. So we're just substituting in for these two things. At A, we've got 1.16 times 10 to the minus 6 over 4 pi epsilon naught times 2.06 minus, for VB, same charge, 1.16 times 10 to the minus 6 over 4 pi epsilon naught times 1.17. Okay, now if we substitute in 8.85 times 10 to the minus 12 for epsilon naught, we can enter all these numbers into the calculator and get an answer. When we do that, we get minus 3,850 volts, which is minus 3.85 kilovolts. So that's the answer to A. Now part B says repeat if point A and B are located as in figure B. So what we've done now is we've moved B so that it's the same distance, but it's now at 90 degrees to A like this. So this is now 1.17 meters. But you'll notice that the potential difference is a scalar. It doesn't depend on where in space the charge is located. It only depends on the distance from the charge, and we haven't changed the distance from the charge. So the answer to VA minus VB is going to be the same, minus 3.85 kilovolts, as we haven't changed any of the distances, we've only changed their arrangement, and this is not a vector. Problem 8, which is for 1, 2, 3, 1 only. Okay, in this problem, we've got two uncharged conducting spheres with radius r. So r is the radius there. That's r. They're connected by a wire. Okay, so here's our wire. The distance between the spheres is L. So this distance here is L. And then we hold a positive point-like charge here, plus Q, a distance R from one of the spheres. And we're told that L is much bigger than capital R, which is much bigger than little r. And we're asked to find Q, which is the charge induced on the conducting spheres. Okay, let's list everything that we know about this problem and then work out how we can use that to write down a formula. What we know is that the two spheres are connected by a wire, and any 2 points in a circuit connected by a wire have the same potential. So that tells us that the two spheres are at the same V as they are connected by a wire. So let's call this one sphere 2 and this one sphere 1. We've got V2 is equal to V1. Okay, now these are conducting spheres, so there is no electric field in them, which tells us that the charges distribute evenly over the surface. And let's just have a look at what the charge is. We know that because they're connected by a wire and they're initially uncharged, then any charge which leaves sphere 2 must end up on sphere 1. So any charge leaving sphere 2 ends up on sphere 1. So this plus Q is going to induce some negative charge on this sphere, and we'll get the same magnitude positive charge on sphere 2. Okay, so what we can do is use this formula here. Let's look at the potential at 2, meaning the potential in the middle of the sphere here. So we've got 3 contributors to the potential here. We've got the charge plus Q spread over the surface of the sphere. So in that case, that is equal to Q over 4 pi epsilon naught, and it's at a distance r. And then we've got the charge minus Q, which is a distance L away. So this is minus Q over 4 pi epsilon naught L. And then we've got this charge plus Q, which is a distance L plus R away. So plus Q over 4 pi epsilon naught and L plus R. So that's our voltage on this in the middle of the second sphere. Let's look at our potential in the middle of the first sphere. We've got the charge minus Q, which is a distance r away. And then we've got this charge plus Q, which is a distance L away. And then we've got the charge plus Q, which is a distance r away. And what we're asked to find is Q, the charge induced on the spheres. So let's gather together on one side all the capital Q terms and on the other side all the little q terms. What we can do is cancel out all these 4 pi epsilon naughts. They're a common factor to everything, so let's get rid of them. Okay, so when we move this over here, we've got 2 capital Q on little r, and then when we move this over here, we've got minus 2Q on L. And let's move this one over here. We've got little q on r minus q over L plus r. Okay, so let's write this one as 2q outside of 1 on r minus 1 on L. And this is equal to little q outside of 1 on r minus 1 over L plus r. And so this is 2q outside of, giving it a common denominator, RL, L minus little r is equal to little q outside of R, L plus r. This is L plus r minus r, so those r's cancel out. Okay, we're just going to continue up here. Let's get q by itself. So we've got q is equal to little q times L times this thing on the bottom, which is the RL, over, we've got RL plus R from here, and then we've got to divide by the 2 and the L minus R. Okay, so this is equal to QL squared R over 2R L plus R L minus, sorry, that's a little r, not a big R, that's a little r. Okay, now that's our exact answer, but now we can make use of this thing here. So because L is a lot bigger than R, this is negligible. Because L is much bigger than little r, this is even more negligible. So this is equal to approximately QL squared R over 2RL squared. These cancel out and we end up with QR over 2 capital R. And so that's our final answer.